In this circuit we're going to add the subnormal numbers into our Logisim circuit. So if you go into the resources section, you'll see the Logisim file, and you can go ahead and open that up and make sure you're on the top level. Now there's quite a bit of change between this circuit and the previous circuit, but we'll take our time and we'll work our way through it. Now the top level here is exactly the same, there's no change, so we can head into the next level down. So in this video we'll cover the far section, and we'll talk through the changes we've had to implement in order to allow it to work with subnormal numbers. Now if we start off here up with the splitter, you'll see that the splitter is really much the same, but there's an extra little section added here, and you can see here that we've taken the exponent values and we've added an extra bit onto them. So these are the unbiased exponent values that we get in, and we've changed it from an 8-bit value to a 9-bit value. So what we've done is just added on the most significant bit. So if I head in here and I'll put a probe on, you'll see that all it's done is added an extra bit on. So the original bits would have been these 8 bits here, so this would have been the least significant bit, and then it would work its way up. And what we've done is we've put another bit into the most significant space. Now this is a known technique, and they actually use this in some floating point adder and subtractors. And we did use this technique as well whenever we were doing the multiplier. So we'll talk through later on why we're doing this, and it'll become apparent why it is we're adding this extra bit. It just makes the design and the circuitry here an awful lot easier. But it also means that we're going to have to change the entire circuit all the way through, and everything that was an 8-bit for the exponent now has to be changed to a 9-bit for the exponent. So if you're building this by yourself, you'll have to go through and change all of the exponent values from 8 bits to 9 bits, and all of the tunnels and all of the blocks that you actually use for your design. So that's the splitter. There's no change in the add and subtract button. If you get into the difference in the swap, now first of all I've simplified this section here. So originally this was joined together, but now what we're going to do is just have the exponent swap. So this tests whether there has been a swap, and it tests whether the EX is less than EY. If it's less than EY, then we know we're going to have to swap it, because we want that exponent value EX to be larger than EY. And that just tells us whether there's a swap. And also it tells us here what the difference is between EX and EY. But note we've got small EX and small EY because these are different values. This one over here is the unbiased exponent, and this over here is the biased exponent. Now the swap occurs exactly as it did previously, but you might note between this example here and the previous ones that the actual naming or the nomenclature is changed slightly, so don't get confused about that. The circuit's still the same. I've just changed some of the names of these tunnels to make it a little bit simpler as we move on. Now the main section here that's changed are these sections here. So we said that we wanted to find out whether the input is a normal input or a subnormal input. We know it's a subnormal input if all of the exponent values are 0. So we take the value for our exponent out, and then we work out through an OR gate whether it's a normal or a subnormal, and we do the same for our Y value as well. And you'll see here that we're going to have the test here for normal or subnormal, and these are outputs, and we'll call them nx and ny. So if nx and ny are equal to 0, then there's the values of numbers that are coming in are subnormal. If nx and ny is equal to 1, then the values coming in are normal numbers. So of course you could obviously have two normal numbers coming in, two subnormal numbers, or a normal and a subnormal. Now the other part here is creating the biased exponent. So we said here, in order to create the biased exponent, so this is a biased exponent here, that's small ex. We take the unbiased exponent, so that's the actual number that you get in for your exponent value. We take away the bias. Now the bias here for a 32-bit is 127, so we take away the 127, and in order to test to get the correct bias, depending on whether the values are, the inputs are normal or subnormal, we have to add on this plus 1 minus x. Now we talked about that in the last video. So all this is here is the implementation of this. So we take our value for our ex, which is this value here, and then we subtract off the bias. Well, that's the bias there, 07e in hex, and then we take the value for our nx and we extend it and we subtract that value off as well. So if you put some probes in, you'll see that this here just follows this. Now it's a bit simplified because what we did was I took the 127 here and I added it on, which will give us 128, and then take away the I took the minus 127 and added one on, which gave us the value of our minus 126. So if you follow, put a probe in each of these spots here, you'll see that this just generates this value for our biased exponent for ex and also for our ey. So that's that covered. So let's start working our way down the far path. So if we get into the shifter, now the shifter hasn't got any changes at all. As long as we use the biased exponent correctly, then we don't have any other changes in the shifter, other than the fact that everything, as I said, has to be a 9-bit. So that has to be 9-bit, and this here has to be 9-bit. So all of the tunnels and all of the components have to be now through this EX route here have to be 9 bits, but the actual circuitry has still just remained the same, and so has all of the rounding, so there's no change there. Now we can head down into we'll leave the sticky bit for now. There's no change, right? There's no change in the sticky bit there, so we're just leaving the sticky bit as it is. As I said, we're not changing any of the rounding here. Now we can also head down into the adder. Now again, there's no change in the actual add and subtraction. It's exactly the same as it was previously. Now the change that we're actually interested in is going to occur in this normalization section. Now it's pretty much the same, other than the fact that we have this extra circuit down here, and we have this extra OR gate, and there's an extra tunnel here as well. So let's quickly talk through why we have these extra components. Now we've seen these truth tables before, so we've seen this one here for the addition, this one here for the subtraction, and we've seen this little truth table here that we generated in order to control the multiplexers, which are choosing the value for our MR and MR divided by 2, but we won't get into that here. What we're interested in is just this one little extra table here for addition. So addition for the subnormal numbers will work exactly the same way as the addition for the normal numbers, as long as we ensure that we have got our correct biased exponent. But there's only one difference, and there's only one anomaly that we have to take care of. And that is whenever we add two subnormal numbers and get a subnormal result. So whenever we do that, what we'll find out is that in order to get the correct exponent value, we're going to have to subtract off 1 from the exponent. So previously with the additions, there was always either the exponent get passed out or the exponent plus 1. But for the subnormal addition, where we've got two subnormal numbers, and when we add them we get a subnormal result, we're going to have to take 1 away from the exponent, but the mantissa still remains exactly as it is. So we'll go into the circuit and we'll see how we've implemented this here, and whenever we get into the circuit we'll actually put some probes on and we'll see this actually occurring. So from this little truth table here, the extra test that we need to make is that nx and ny are both zeros. That is, it's a subnormal input. And if bit 24 is also a 0, then we subtract 1 off from the exponent and leave the mantissa as it is. So let's go ahead and we'll see that. So I'll make the circuit just a little bit bigger so we can see what's happening here. Now we said that we're going to have to test and see that we have actually got two subnormal numbers coming in, and we can test that we're going to get a subnormal result. So if the nx and ny are both zeros, then both of these lines will go high, and it tells us that we've got two subnormal numbers coming in. Now we're working through addition here, so we've got a test here just to ensure that it is actually addition we're performing. So if SZ is 0, then we know we're performing addition, so that goes high. So we've got a high input here. Now the other test we're wanting to go through here is the test for the result. So if the bit 24 is high, then we know that the result is going to be a normal result. And if bit 24 is low, we know we're going to have a subnormal result. And we'll be able to see that in the spreadsheet. So this little truth table here, this little realization tells us that we're getting two subnormal numbers coming in, and it tells us we're getting a subnormal number coming out. And we've called that sub_norm. So we said that if that was the case, and if this subnorm goes high, then we said that we're actually wanting to change the exponent value. So rather than doing an addition and having just passing through the exponent value or the exponent value plus 1, in that one instance, and only that one instance, what we're going to have to do is we're going to have to pass on EX, that's the exponent value minus 1. So we can see here that for that addition, we can add on an extra OR gate here, and we can do the test. So this will provide us for the test. So if that goes high, it tells us that we've got a sub plus a sub giving us a sub, and that means that it's going to choose the value 1, and it's going to pass this value here, which is EX minus 1, through to the outputs. Now another little thing to notice here as well is that what we've had to do is we've had to add in the addition of the unbiased, the addition of 127 in order to take the biased exponent, small er, and produce the unbiased exponent, which is large er. So that's what this little extra block here is for. Now there's no change here for the MR value. The MR value still goes out as it was previously. So that's pretty much the biggest change that we're going to see for the far side. So if we head up into the top level, we'll just cover a couple of other little points here. Whenever we head into this concatenate section, you'll see here we're going to have to then strip off the most significant bit. So again, when we strip off the most significant bit, it goes from a 9-bit here to the final 8-bit output. And also we strip off the most significant bit in the mantissa to provide us only with the 23-bit number. And then we join these together with the sign to get the final answer. And that final answer then gets passed through the rounding section to the output. So that covers the only difference that we see whenever we add subnormal numbers in and we're doing addition. And the only thing we have to remember here is the only change is if you have a subnormal number plus a subnormal number giving a subnormal result. In that case, we need to take one away from the exponent and the mantissa can remain the same. So I suggest you put some probes in and you test this. So let's have a quick look at it in the Excel spreadsheet. So what we want to do is we want to put in two subnormal numbers. So what we can do is we can put in the smallest subnormal numbers. Now I've got a file here that I tend to keep that's just got some of these numbers here handy. So you can see here we're going to put in the smallest subnormal number. Okay, so I'll put that in just now. And we can do the addition. So we can go Control V. So that's the smallest subnormal number. And we can see it's actually the smallest number that we can create. So that's that number 1 here. So it's 1e to the minus 45. So the 1 plus 1 is going to give us the 2e to the minus 45. So what we want to do is go ahead and put these numbers in to our Logisim. And you can see I've actually already got these numbers here. So that's going to be a value of 1 and a value of 1. And when we add it out, we get this value of 2. So when we head back in here, now what you can do is you can stick some probes on the exponent values here, and you can see that indeed we're going to have to subtract a value of 1 off in order to get the correct answer. So if we were to stick the probe into the value of EX, then you would see that the value here for our EX is actually the biased exponent. Okay, so it's the EX and we've had to take away the value of our bias and add on the 1 plus NX. Okay, so whenever we head out through here, you'll see that if we didn't have that extra subtraction of 1, the value here would be out by a value of 1. Instead of getting the final exponent value as all zeros, we would end up with an exponent value of 1. So again, stick the probes in and check through, and you can see that that does actually occur. So I think that's all for this video. In the next video, what we'll do is we'll head back in, but we will cover the near side and we'll see the differences and what we've had to do in order to get it to work with subnormal numbers. So thank you for listening. I'll get you on the next video. Goodbye.